In this video, we're going to discuss continuity. A function is continuous if the limit as x approaches c of the function is equal to the function at that point c. Let's look at some examples of things that are not continuous to get an idea of what we're dealing with here. And I'm going to start with graphical examples because much in the same way we did limits, if we start with a graph, we get an idea what the picture looks like. I think it's a little bit easier. So let's take a graph. It's a simple line, but it has a hole in it. Obviously, this is something that is not continuous. If we're to look at this value right here, let's call this value of 1, the function doesn't exist. So sure, it has a limit. Limit value is whatever that y is. But because we see right away the function doesn't exist, this is not a continuous function, or we could say it's discontinuous. And I'm going to label these as we go along. The reason that this one is not continuous, or the point at which it's not continuous, is this point, the hole. Let's look at another slight variation on this. So again, we have what appears to be a hole, but this time I'm going to place a function value above it. So we can see that at whatever x value this is, say 1, that we have a limit. We can also see that we have a function value, but because the two things are not the same, our limit is 1, our function value is 2, this is another discontinuous point, and we would say that this one is a removable discontinuity. So similar to the hole, but because we have that function value, it's not continuous for a different reason. We didn't have a function value, now we do, but it's not the same as the limit. Of course, if we have an asymptote, this is something that is also not continuous. So at 1 here, we have what we call an infinite discontinuity because we are going to infinity. And so this one fails on 3 accounts. The limit value fails to exist, the function value fails to exist, and the two are not the same. Remember, even if they were going to say both up, both to infinity, infinities are points that fail to exist. If we have two things that don't attach, so for instance, this example, once again at our point 1, we can see that the function exists, it does exist, but because the limit doesn't exist, we're going to, this upper value, we'll call it 2, and this lower value of 1, depending on which side we come from, this is also a non-continuous function at 1, and here this is what we call a jump discontinuity. And then one last type that we might see. And sometimes functions, when they get really close to a certain value, they just start oscillating so quickly that we can't even tell what's going on at certain values, right? So as this is getting super close to 0, it's just oscillating so much, and then it starts to spread back out on the other side. And so this is what we would call an oscillating discontinuity. Where things get unstable at a certain point. So somewhere in here, it's getting unstable at the -1. So these are the things we want to be on the lookout for. However, if we're going to state why something is discontinuous or not continuous, we're not just going to use the name. I want to see that we are formally stating the reason why. And that brings us to our test for continuity. 3 things must be true to be continuous. So the first thing that must be true, the limit value must exist. And I should say these are to be continuous at a point. So we're testing a single point in these cases. Limit value must exist. 2, the function value must exist. And then 3, the limit value must be the same as the function value. If any of these 3 points fail, then we'd say the function is not continuous at the point, and in order for a function to be continuous, it must be continuous at all its points. So these are going to be our three tests to test whether a function is continuous at a point. So for instance, we'll take one more graphical example and then we'll get into some algebraic examples. Let's say, we have something looks like this. Try and make that match up. We'll give that a value of 1, that a value of 1, and then restarts down here at 1. So if we're to go through the tests, does the limit exist? Well, right away we see no. We have the two-sided limit failing to exist, because if we were to look at the limit as x goes to 1 from the left, and we'll name this function f of x, well, that limit would be equal to 1. The limit as x goes to 1 from the right, well, that's equal to 0. And so the limit as x approaches 1 of our function does not exist. So this would be the level of formality I want to see when we are showing whether a function is continuous at a point or not. We not only say the limit doesn't exist, but we're showing why that two-sided limit doesn't exist. Of course, if a function value fails to exist, so maybe we just have a hole, we could just say f of x fails to exist at 1. So let's look at some equations. Let's get into the algebraic side of things. So let's take the function 3x squared minus 2. If I think about this function, I know what this function looks like. It is a quadratic function. It's a parabola. It is going to open up. It's going to be shifted down by 2, vertically stretched. We get a pretty good idea what this looks like, and that's why a lot of times I like to start with the graphical ideas, because once we know what something looks like, we have a pretty good idea what it's going to do. But there are no values that I can think of here for which a function fails to exist or for which the limit would fail to be the same as a function. So this thing is continuous. And we actually have a theorem in our book that says polynomial functions, they're continuous functions, because we know that all of their function values equal all their limit values. So this quadratic is also a polynomial. Quadratics are polynomials, and therefore we know it's continuous. Let's look at another function. Let's call it g of x. And this one is 5x minus 2 over 3 plus x. This is not a polynomial function, so I'm going to give it a little bit more thought. And again, I'm thinking about, does the limit exist? Does the function value exist? And are they the same at all points? And right away, I see that it has a denominator. And we know that rational functions, we can't have 0 in the denominator. And so if I set that denominator equal to 0, I see that at -3, we'd have 0 in the denominator. That means g of x fails to exist at x is equal to -3. Therefore, without giving it any more thought, not looking for any limits or anything like that, we can say that g of x is not continuous. Continuous, I'm going to abbreviate CONT at x is equal to -3. We also know a little bit about rational functions. We know that that would be the only point at which it would be discontinuous, but we know that g of x is not a continuous function across the domain -infinity to infinity. Now, I've talked about when we're continuous at a point, but I haven't actually talked about what it means for a function to be continuous. So let's do that next. A function is continuous, not just at a point, but at the whole function. A function is continuous if it is continuous on its domain. On its domain is key here. If we think about this g of x function, what was g of x's domain? Well, its domain was from -infinity to -3, -3 to infinity. I'll write that out. Domain was -infinity to -3, and then -3 to infinity. And so that tells us that even though g of x is not continuous at this point, g of x is a continuous function. So notice just a few minutes ago when I said g of x is not continuous, I was very specific. I said at that x is equal to -3. Then when I said g of x was not continuous, I defined it's not continuous on the domain negative to infinity. But that's not its domain. If I were to say, is g of x continuous from negative to infinity? No. Is g of x continuous on its domain? Yes, it is, because its domain already excluded that value. Now, does that mean that all functions are going to be continuous functions? Because how could something not have something inside its domain if it just didn't exist there? Well, no. One of the most common examples of this are piecewise functions. So let's think about the piecewise function. We'll call it f of x. X plus 2 for x less than 0, and the square root of x if x is greater than or equal to 0. What is the domain of this function? Well, clearly, negative to infinity. We have all x values here, all x values less than 0, and then we have all that are greater than or equal to 0. We know that this is this little piece here, the x plus 2, that's a polynomial function, it's linear. That would be continuous on this restricted domain. The square root of x, we know what that looks like. That would be continuous on its restricted domain. The question is, what happens when I put the two together? Is this f of x still a continuous function? Well, we know that its domain includes all real values. Does it include all of its values inside the function? Yes. So any function value exists. We can find f of 2, f of -5, f of 7. Anything is fine. But what about its limit? So to figure out whether its limit exists at all values, let's think about that transition point. That'd be the obvious place for it to break. Let's take the one-side limits. The limit as x goes to 0 from the left. That means we're going to have to use the first equation here. So we'll have 0 plus 2, which is equal to 2. And then we're going to take the limit of 0 from the right, which means we're going to have to use that right-hand side, the square root of 0. The square root of 0 is 0. And so what we've just shown, thus, the limit as x goes to 0 of f of x does not exist. And since the limit does not exist, then f of x is not continuous at x is equal to 0. And because this time x is equal to 0 was in the domain, well then f of x is not a continuous function. So now we have had two examples of a function failing to be continuous at a point. But in the first example, the point was not included in the domain, so we can still say the function is continuous. The second example, because the point was in its domain, it's not a continuous function. It breaks at that center point. Let's take one more example. I'm going to use another piecewise function. Take h of x to be, we'll do x squared plus 2 if x is less than 0. 3 if x is equal to 0, and the square root of x plus 2 if x is greater than 0. So we look at this for a second and say, well, domain clearly all real numbers. We can plug anything into this x squared, so we're going to have all those values less than 0. X equals 0, of course, we can have 3. X greater than 0, that one, that's all set too. So our domain would be negative infinity to infinity. Furthermore, I'm pretty confident that we can find the function value at all these points. That's not going to be a problem. So I'm not even going to bother looking, right? We only have to find where it fails to show this is not a continuous function. So I'm going to immediately jump into the limits. And again, I think 0 is the point at which it breaks. So I'm just going to concentrate on that 0. Let's take the limit value as we head to 0 from the left. We called it h of x. And so that means I'm going to use that very first equation. So we'll have 0 squared plus 2. And that's equal to 2. Then I take the limit on the right side. Limit as x goes to 0 from the right. of h of 0, or rather of h of x using the square root of x plus 2. So square root of 0 plus 2, well, that's equal to 2 as well. So we can clearly find h of 0, that's just 3. We found the limit. We can now say with confidence that the two-side limit exists. The limit as x goes to 0 of h of x is definitely equal to 2. But remember, we have to test that third criteria. Are these two things the same? And we found the limit to be equal to 2, the function value to be equal to 3. And so then we can state with certainty h of x function h of x is not continuous at 0 because the limit value does not equal the function value. Just like we said in the last case, because the domain was all real numbers, that means 0 is included in the domain. The function h of x is not a continuous function. If we're to try and name these types of discontinuities, right, with our function f of x here, this was a jump because we see that those limits are going to two different places. That would be a jump discontinuity. This example down here that we've just worked with, this would be a removable discontinuity. Those two things do touch on both sides. It's just the one point has been removed. And then in our first case, this was an infinite discontinuity. It's one of our vertical asymptotes. And so that gives us a pretty good idea of how we're going to look at continuity. We need to find the limit value, the function value, and make sure those points are the same.